Greetings from IIT Kanpur. Welcome back. So, today in this discussion, we will talk about enablers of VLSI in terms of the processing technology. First, the disclaimer. Now, over the last several decades, various technological processes have come into play which earlier could not even be imagined. And or even if it was known, it was never known that you could use it this way. So, the VLSI technological field as it advanced was supported ably by various processing technologies. Let us take a quick peek. So, advances in technology, in processing technology, if you look at it, one of the key enablers, one of the main reasons this was possible is the precision with which we could control various parameters that were involved. Even normal simple things which often become simple once it's available, we don't think twice about it. The ability to control vacuum. Very comfortably you can go to really low vacuum pressures. Of course, for ultra high vacuums you might have to do some extra effort, but that's still possible today. So, vacuum, temperature control, very precise temperature control. So, when you are oxidizing silicon, for example, because you are sure 800 degrees is 800 degrees and not 802 or 798. So, that means you have very good precision of control, and that means you are able to predict very exactly how much oxide is going to be formed. And you can set the temperature and also control it within that range. Flow rates of various gases, and also environmental control. Okay, the environment where which we are fabricating, I'll mention a little bit more later on this as well. And this has allowed for very predictable processes. This could not have been done unless this level of control was possible. You may have the schemes to implement, but if it's not controlled, every time you do, if it's something different is happening, the technology will not progress that fast. Of course, you'll have to come up with innovations, but the processing technology precision is what has helped us. Some of these have been at molecular levels and atomic levels is mind-blowing. For example, molecular beam epitaxy, you deposit and develop materials layer by layer, a single atomic layer by a single atomic layer, you are able to deposit it. So, this allows you to mix and match. For example, if you want to make silicon, germanium and all that, with a very precise ratio of silicon and germanium, you are able to do that. Newer technology, atomic layer deposition using wonderful chemistry. So, so these are some things that have really been a game changer. Plasma assisted processing. You can do things which are supposed to be done at higher temperature at much lower temperature, and that means that the thermal budget is greatly saved. So, that helps in ensuring that you are able to push the other aspects of the processing for better performance and yield. Ion implantation, some of these were known, accelerating an ion and so on was well known, but its use as a technological tool to very precisely put the number of atoms or a number of ions at a particular place, and that were with very high predictability using the help of statistics has really helped, especially doping and so on. And in fact, it has reduced the thermal budget. Newer technologies, chemical mechanical polishing, etching or removing material. Wet etching used to be popular, but nowadays dry etching has come in, and you are able to control how you are etching. Has it got to be isotropic or anisotropic? You can make even very interesting shapes with very high aspect ratios. I'll just flash some of the images of some of the processes that are there. So, this is one of the earliest in terms of in the silicon technology space, silicon dioxide formation. Now, this is remarkable because you are able to get precisions of the order of nanometers of oxide. Remember that you are just talking about, say, 220 molecules or something of that order, okay, molecules, and very precisely over the full wafer, over zillions of wafers, to ensure that your transistor threshold voltage and other properties are well within the range of what is acceptable. So, this is a very precise process done in very clean environment and with very excellent control of the temperature as well as the gas flow rates. Molecular beam epitaxy, I mentioned about this a little while earlier about how you can make layer by layer material, and sometimes you make use of these to do some small engineering as part of your VLSI fabrication as well where required. Of course, some of these can slow down your throughput, but maybe for starting materials and for allied technologies, this plays a very important role. Ion implantation, as I said, what is remarkable about this ion implantation, as I mentioned, ion implantation was known, but by accelerating the ion very precisely, controlling the current is something electrical engineers all have learned how to control very precisely. So you can actually decide how many ions you are putting inside this. So it is well within some of the best resolutions in terms of best accuracies of doping you can get with ions, and you can also put it where you want, precisely in the region that you want. You are able to put, and with the help of statistics and other learning simulations, you can predict exactly what is happening. And that being the case, this has really helped. So it seems to be a very simple technology. All that you're doing is accelerating an ion and making it implant, but the nuances that are there all have been very well studied, and that has helped us really make tremendous strides in VLSI world. Plasma processing. Plasma, many of you might know, is a fourth state of matter. It's all there in a lot of places, but typically in thermal equilibrium plasma, if you are going to use, you need to go to very high temperatures for processing. So what you end up doing is, and that those temperatures, nothing will sustain, everything will melt, right? So, but here what we are doing is, we are getting a cold plasma, as it is called. Using a cold plasma, you just make sure that the electron is at very high temperatures, and with the help of that, you are able to do a lot of process engineering, and including depositions in etching and various source of ions, lot of source of very high quality ion, purity ions. So this is a remarkable technology which has helped VLSI, and not just that, it ends up becoming a dry process. Dry process means that some of the contaminations and other things can be reduced. Of course, some other contaminations may come in as well, but and also it can be done all in vacuum environment, and so also a lot of control can be there. Dry etching, as I said, of course, sometimes plasma is used in some of these. If you look at etching, you are able to get very high aspect ratio. So if you look at this particular example, this is something I took from the net. 17 micron is the depth, but the surface is 0.2 micron by 0.2 micron you can etch, and it can do it reproducibly over millions and millions of trenches. For example, you are making a trench DRAM. So this level of control that you have, and not just that, you can sometimes make it bottled etch, that is, you etch anisotropically and then you etch isotropically, so you'll get a bottle shape and so on. So these things have played a very important role, and of course one cannot not leave by the discussion on technology without talking of lithography. In a way, this defines the technology. We saw that the gate length defines the technology. The gate length is ensured with the help of advancement in technology, advancement in lithography. Lithography over the years has really advanced steadily. Whenever there was a problem, all the brightest minds came together, they worked it out, and they were able to overcome it. Today we have extreme UV, high numerical aperture lithography tools which can get resolutions of almost 8 nanometers. And of course, you use some other tricks to get the channel length corresponding to or equivalent to the 3 nanometers and so on. So you are able to achieve all this today, and this is something that from Intel's website I took. So clearly, technological advancement has been the cornerstone of VLSI development, as one of the cornerstones. There are many cornerstones, and this has certainly played a very important role, and the advancement which you could not even imagine even a couple of decades ago, you are able to achieve it, and with time it's only improving. So technological advancement allows precise control of what you are doing, and that means it's very predictable. If it's predictable, you can plan accordingly and get what you want. And not just that, many novel approaches have come up over time. In fact, what was assumed to be non-physically feasible, you end up making the stuff. For example, ion implantation, you're putting an ion some deep inside the material, and at the end of the process, with all appropriate correction factors and all, the surface is as though it is undisturbed, and only you find something deep inside. So these are remarkable technologies. And similarly, plasma process. There's just a couple of examples, but many of them have come over time. And actually, thanks to the research and development that is taking place in labs around the world, and including industrial labs, which play a very important role, technology so far has managed to deliver whatever VLSI needed. So the roadmap said that the next technology node is supposed to be, say, now it is 3 nanometers. Technology is able to provide what is needed to get that. So as an enabler, it is one of the very obvious things that really comes up. So with that, let's go to the next enabler, which is the characterization tools. One thing is to make the device. That's where the processing tools are needed. But as you are making the device, how do you make sure you are doing the right thing? Or after you have done, how do you make sure you got the right thing? For that, you need characterization tools. So this actually, as one of my colleagues, Professor Mohapatra, tells it very colorfully, these are the eyes and ears that you have during processing. When you are doing processing, these are like your sensors that you are able to know whether something has happened or not happened. So the characterization tools, like technology, has also advanced, especially the various ideas that have come, how to use some phenomena in order to be able to make an assessment. For example, the optical properties is sometimes used for finding the refractive index. This is something very well known for a long time. So such things can be used to do in situ measurement. As the thing is being processed, you can use optical techniques and so on to characterize material. And they may be deployed in the process line itself, and that really that allows for a feedback loop. If something is off, you can immediately correct it rather than the whole batch comes out and you go back and try to do the next one. So you can correct it on the fly, so losses are less. And also various amazing characterization techniques have come. This is like a alphabet soup, right? So many acronyms, but these are all well known in the VLSI world. Scanning electron microscopy, high resolution transmission electron microscopy, then atomic force microscopy, X-ray diffraction, scanning tunneling microscope, secondary ion mass spectroscopy, and the list goes on. Many of these are for material characterizations, which earlier you could not do, maybe 100 years back. Many of these things was not, you could not see. For example, you couldn't see the atoms, within quotes, see the atoms. Today you can actually see it, and in fact, some of the technological facilities can be made into desktop, like atomic force microscopy. Of course, you look at the surface there. So these advancement has been amazing. While material characterization is amazing, electrical characterization is no less amazing, and sometimes I would say more amazing, because maybe I am an electrical engineer. So the precise and quick measurements of resistance, inductance, and capacitance, that is the essence of electrical engineering, electrical measurements. Sometimes optoelectronic measurements comes in with the shining of light, what you do. So low temperature measurements in some cases, you can actually get some information almost sometimes at the atomic level. Then optical characterization, optoelectronic characterization often optoelectronic rides on the electronic as well. Ellipsometry is purely optical, alignment tools. In fact, now it's all automated. So you have a huge wafer, and how do you know you are going to precisely that particular location? With optical characterization tools, you use feedback and you are able to get there very fast. Optical mapping and so on. And again, this ... hides a lot than what I have shown. So clearly, characterization tools have played a very important enabling role. So let me also flash some images of some of that technology. This is just a representative sample. Clearly, this is something that just came to my mind. Not that they are necessarily the most important, but they are important, no doubt. So atomic force microscopy, whenever you wanted to measure the surface in atomic resolution in the z-axis. So and if you look at it, in fact, this technology came about when I was in high school. Okay, so it's amazing to see that during our lifetime, ideas have fructified into actual products. And today atomic fiber microscopy is found in almost all many of the institutes around the country as well. Transmission electron microscopy, here I am showing a sample of something that I did during my PhD, but here you can see that this silicon, you can see the crystallinity of the silicon, that a piece of from somewhere in this location has been analyzed with transmission electron microscopy. So you prepare the sample and allow electrons to go through, and from the image you recreate and find out what is happening. So you can see the crystalline structure of the silicon, and we have made an oxide here, and you can see the oxide is amorphous, and you can see the quality of the interface. So this almost atomic precisions you are able to see, and these things have only improved over time. Secondary ion mass spectroscopy, very important to find out precisely how much doping was there. You have cesium ions or something that is bombarding, and the secondary ions that come out, they are analyzed with mass spectroscopy, and you can find resolutions of the order of tens of nanometers and precision of parts per billion. Okay, I'm just giving some examples of how the various dopants are distributed in a particular silicon. Okay, so you can actually see sometimes that if there is, you have a silicon which is purely p-type or is compensated p-type. Okay, so those make a difference in terms of lifetime and so on. So you can actually find out a lot of information from SIMS. Of course, some of these are destructive, so you have to know how to take out samples and you do the measurements. Then comes electrical characterization. I'm giving just a broad overview. Electrical current is something that we can measure with higher precisions, and if you look at it, we have attoamperes which can be measured. Okay, attoamperes 10 to the minus 18 ampere, and note that electronic charge is 1.6 10 to the minus 19 coulombs. That means of the order of 10 electrons crossing through a cross section per second, you are able to measure. So that's the level of precision we have been reaching. So it's mind blowing. And capacitance, again femtofarads you can measure. This is important because your devices are becoming small and you want to see and understand the capacitance, parasitic capacitance and so on. 10 to the 15 farads. Voltage you can measure up to 0.1 millivolt. This is remarkable considering that at room temperature your thermal noise is going to be 26 millivolt, right? So that being in the case, you are able to get below the thermal noise. Of course, you have to do special preparation for that and etc. And all these and other electrical characterization as well as frequency and capacitance voltage measurement, all sorts of impedance spectroscopy. The list goes on, which have developed over time, and they are and not just the technology but also how to analyze them. So they are all ably assisted by automated measurement setup. That's what has helped us. So the takeaway of characterization tool for VLSI, I would say something similar to what we said about the processing technologies. The precision has gone up, and as a result, you are able to tell exactly what is happening. It is not approximately, or there is not too much noise, so you have to build that in your analysis. You are able to get lower and lower factor of noise, and you are able to measure it more and more precisely. And then the cost of characterization also has dropped. This is something really remarkable, and often it is thanks to the progress in VLSI technology. Because of progress in technology, they have made more and more sophisticated equipment. So the somewhat less sophisticated equipment end up also being at a lower price, and that becomes accessible to a lot more research groups which can use it to make more advancement in VLSI. And thanks to R&D, again, characterization technology has continued to advance. And this is in step with what is the requirement of VLSI industry. So often what happens is, what is needed for VLSI industry, there is a lot more focus because clearly a lot more resources are available, and that ends up developing this those types of characterization even more. But usually there is a secondary effect, and as a result many more characterization technologies come, and of course creativity is the limit. People come up with newer ways of characterizing electrical material, optical properties. Now we come to the enablers, which I would say supporting technologies and factors. Sometimes we don't think of them too much. They are an afterthought, or maybe they may be there but it's in the background, but they played a very important role. I would like to mention a few. I'm sure there could be a few others, but first order I feel these are some of the important factors. We talked about the cleaning, the processing environment. The technological progress that has happened in terms of clean room implementation and often driven by VLSI industry has been remarkable. In fact, clean rooms are also needed even in biological applications. You want to make sure that some infections are not there, so you want to keep out any viruses or anything like that. But in clean room technology, for VLSI, the requirements are even more stringent. In fact, some of the state of the art are class 1, they call it, in the old traditional thing, which means that there is one particle you are allowed at most. Ideally, no particle, but if you are making a measurement, one particle of size greater than 0.5 micrometer per cubic foot. That's what is needed. That's what is allowed. And of course, 35 less than 35 particles of size 0.1 micrometer. So if this is there, you call it a class 1 clean room. These are some of the most advanced clean rooms. In the newer standard, it's called ISO 3 clean room. But that being said, many of the applications may not always require, the certain processes in VLSI are extremely critical. There you have to have the best clean room that is available. But certain processes are more forgiving, and the fact that they are the clean rooms are available now may not be to that stringency, but some other stringency some other processes gets a chance to be developed in labs across the world. So clean room has played a very important role, and we have many clean rooms today in India, especially in the last couple of decades, for the science and technology labs. The other area that is very important is controls. Robotics plays a very important role, and not just that, the whole lab, over time everything is automated. Gone are the days when individuals, humans, used to carry these wafers for various processing. All these are done with robotics. That means they are predictable, they'll put it at the precise location. There are of course ways of checking that and ensuring that there is less harm for humans also. So you are able to be bold enough to try even more challenging processes. So robotics plays a very important role in VLSI world. This is a robotic arm which is handling a box of wafers. There are some wafers in this box at the bottom. And if you go to any modern fab, some of the latest fabs, you'll find very few humans. You can see these boxes on the top. These are huge wafers, maybe 300 mm to 450 mm. And in fact, humans to lift it itself is challenging, because there are about 20 to 25 wafers in a cassette. So, but these are all moving on the top using robots and automation, complete automation. So from one location where one process is to be done, it goes, and these are all, the queue is set up. So there are of course humans out there who help ensure that, but even that is becoming more and more automated. How to set the queue so that you optimize the whole process. So in a very short time, with higher precision, with less danger to humans, you are able to achieve all this with higher predictability. So the controls and robotics has played a very important role in VLSI's progress. Sometimes we think where are the mathematicians, but actually mathematics plays a very important role in all processing, I would say, not just VLSI, but certainly in VLSI, because you need the high precision. Statistics has developed some excellent tools in the last century or so. You have methods of design of experiments. Of course, the mathematics probably was known, some of these were known earlier, but to put it together in a way such that you can, if there are multiple parameters, what is the combination of parameters which will give you the best process that you need, for say the thickness of a particular film, gas flow rate, temperature, and maybe pressure and surface properties and so on. So how to reach that optimum? You have mathematical tools like design of experiments with minimum wastage, maximum information. You can actually design these experiments and reach to the optimum process. And besides that, once the process is already set up, how do you ensure that it is on track? Today we talk of Six Sigma process. So these are tools that have really made a big difference in development of fabs, and nowadays they are adopted around the world in all the modern fabs. So you ensure that you are on target and your sigma of your process is within control. And you can actually, by doing proper statistical measures, you can actually, by proper sampling, you can actually know what is happening with the whole process. So in a way, this gives you information, and you can use that to make sure your process is more on track. So all this reduces wastage, and not just that, the time taken to optimize is reduced. So as a result, you can use that time to do other innovations and other sophisticated activities to make advances in VLSI. Of course, no gainsaying this, computing tools. Okay, what is interesting is VLSI, one of the main products of VLSI are computers, but as computers became sophisticated, they fed back and made VLSI process more sophisticated. That led to even more sophisticated computers. But what is remarkable today is, and the place where we stand today, hardware and software have developed to such an extent. Tools like machine learning, artificial intelligence, these are a mainstay on processing. And so much so that really complicated and sophisticated technologies are made in fabs, which are themselves very sophisticated in technology. They are all controlled with modern computing tools and AI. And the role of AI is becoming increasingly important, so much so that you can have predictable results in the most optimized manner. So as a result, the cost is in a way cut down, because all the wastage can be reduced. So AI plays a very important role in today's processing, where every parameters, I read somewhere the number could be off by a few factors, but 40,000 odd parameters are tracked, and continuously anything going off, you make corrections accordingly, so that hardly any of the process that is there in the complex process chain that is there in modern VLSI, you are able to bring it back to track using AI. And of course, this is something that probably is in a way is an overriding factor, the economic policy and political decisions. Okay, so targeted financial incentives, supporting trade regulations, supportive trade regulations, strategic investment in research and development, education, because you need the manpower to do that. Part of the thing that we are doing now, right? So this is important, and also regulations that are there, international relationship and investment incentives. Even as I give this lecture, a lot of geopolitical jostling is taking place in terms of how to manage the resources and what technology will be supported and not be supported. But by having all this in place, we can see that the regions and the players who have these things properly worked out, you end up finding that they are able to get more resources to get VLSI technology ahead. So economic policy and political decisions has played a key role. If you look at the whole development of VLSI, and which countries and which regions and within the country, which companies within that region succeeded, it depends on the economic policy and political decisions that were taken. So it's a very important role, and one should be cognizant of it. And for that, one needs to have a thorough understanding of VLSI technology, so as to give feedback. As individuals in society, we can always give feedback to facilitate VLSI technology. So if I may summarize with the takeaways on the supporting technologies for VLSI, we may not realize it. It is not just electronics or even materials or some chemical engineering. There are lots of technologies actually have supported and are critical for ensuring the success of VLSI. And some of them that I have listed is computers, control system technology, robotics and so on, statistics, the various tools that are there, computers, they all play a very important role. So what it means is, if you want to be a successful VLSI technology person, you should be aware of these areas. You need not be experts in all these areas, but you should be aware of what is possible, what may not be possible, and sometimes the solution may come by just choosing the right statistical tool for your analysis. You may find that you are able to get better success in IC fabrication. Advent of AI is going to be a game changer and the powerful computing that is associated with it, it's pushing the VLSI frontiers, and we are in the beginning stages of that. It ensures high precision and less variation and higher yields. It leads to low cost as well as vastly improved performances, because your tolerance, you can actually squeeze it more. So that means you can afford to design more bold circuits. And then of course role of economics, finance, the source of money for that, politics, political decisions, political will, these play a very important role in the success of VLSI. And ultimately this will define which type of what direction VLSI takes, and which are the places and the entities, individuals and companies that will succeed. So with that, I conclude the discussion for enablers of VLSI technology.